In this video, we're going to introduce another new concept that kind of extends what we think about when we think about matrices and matrices that might be somehow related. And then briefly touch on this other concept that now is going to tie everything together, including the eigenvalues and eigenvectors. So we're kind of building towards something here. Let's focus on the idea of similar matrices. Now, when you hear the word similar, you think of some things that might share similar properties. Like even in terms of words, you might think of words that might be spelled differently, might be pronounced differently, but they pretty much convey the same meaning. Or could be words that are very different in meaning, but they sound alike. So there's certain properties that they might have in common, but then others not so much. It turns out that that's also true for matrices, right? So what we're going to define now is what we mean by two matrices to be similar. So I'm going to write it down and then just kind of explain what's going on. So let A and B be, let's say, n by n matrices. So we're dealing with square matrices here. A is similar to B, so this is what we're defining now, if and only if, so there exists an invertible matrix. So invertible matrix, let's call it P, such that this is true. So if I can express B as a special product that looks like this, P inverse times A times P, then we say that A and B are similar, right? Now, this being a matrix equation, it has a lot of other sort of equivalencies. So let me just write a couple equivalencies here. So let's say we didn't want to express anything with the inverse. If we multiply both sides of this equation on the left by P, this is what it would look like. We would have P times B is equal to A times P, right? So this is basically saying if you do pre-multiplication by of B and post-multiplication of A, then you're going to get the same result, right? Assuming they're similar, right? And then also, if you notice over here in the definition, I have B isolated by itself. Now, if I wanted to take this equation here in green and isolate A by itself, I could then do post multiplication by P inverse on both sides, and then it looks like this. I'd have P and then B and then P inverse, and then that's equal to A. And then let me just kind of do a little sleight of hand here. Suppose I call P inverse Q, give it another name, but then that P would be Q inverse, right? So then like that, and then we would have this, right? So it's basically saying if two matrices are similar, you can write one of them as this kind of special product involving the others, right? And these sort of invertible matrices. So the idea of similarity is these few equations that I've just written down here. It shows that if A is similar to B, then B is similar to A, right? Again, that similarity, just the way we use that word, it kind of makes sense. All right, so that's what it means for two matrices to be similar. Now, similar matrices by themselves are important. I just want to show you exactly, what are some of the consequences of this. And I think we've seen it previously in some of our other matrix calculations. When you think about, for instance, the determinant, you can find lots of different matrices that have the same determinant, right? You could even have matrices of different dimensions that have the same determinant. Well, it turns out if two matrices are similar, then they have to have the same determinant. And here's a quick proof of this. So I'm just going to give you one property. So let's say I take the determinant of both sides of this equation. So the determinant of I'm sorry, let me do the B. So the determinant of B will be equal to the determinant of this product, right? Now, we spent a lot of time, talking about properties of the determinant, and we know that the determinant is a multiplicative property where it doesn't matter if I multiply first and then do the determinant, or do the determinants and then multiply. So I can basically break up this determinant on the right as the determinant of P inverse times the determinant of A times the determinant of P. And then I know that the determinant of an inverse is 1 over the determinant of the original, right? Because again, this is one of our properties that we showed for invertible matrices. Now remember, the determinants now are just numbers, right? These are going to be numbers. They could be complex if you're working with complex numbers. But these are just numbers, so you can multiply them however you want. But more importantly, you're multiplying the reciprocal of the determinant of P by the determinant of P, so that goes away, and then voila, look at what you have. You have just reduced this right-hand side to the determinant of A, right? So two matrices, if they're similar, they're going to have the same the determinant, right? So they don't have to be equal to have the same determinant. But the flip side of that is you could have matrices that have the same determinant but are not similar, right? So you just have to be careful the logical sequence that you're trying to apply there, right? So another property now, so that's the determinant. Another property that's more related to what we're working on now is that if two matrices are similar, then they have the same eigenvalues. Now that's pretty profound, right? So let's see if we can sort of establish that. Here's like a little symbol that you can use to represent is similar to. So a lot of times you might see a little tilde in the context of matrices. This just means A is similar to B. So then let's write down our definition. So that means B is equal to P inverse times A times P. Now, if I want to show that these two matrices have the same eigenvalues, I have to show that, roughly speaking, that they should have the same characteristic polynomial, right? So if they have the same characteristic polynomial, then their roots will be the same. That means their eigenvalues will be the same. So let's see if we can just do a little bit of algebra here and look at the determinant of B minus lambda I, right? So this would be, let me write it this way. This is the characteristic polynomial for matrix B, right? Take its determinant of this B minus lambda I. Now let's start to kind of modify what's in the parentheses, because somehow we want to convert this into the characteristic polynomial for matrix A. So I have something that I can replace B with, right? It's not going to look necessarily pretty, but as I say, beauty is in the eye of the beholder. So I'm going to put the P inverse A P in for B, and then I'll have minus lambda I. Now when I have this is like, I'm pretty stuck here, right? I'm pretty stuck. But I think about the identity. There are lots of things I can do with the identity. In fact, here's what we can do. Instead of writing I can write this as P inverse times I times P. Why am I doing that? One, well, it's true, right? So I'm just basically saying something that's true. I'm all about truth. But then not only that, but I have something very similar in both of these terms, because on the left side, they're both multiplied by the P inverse, and then on the right, they're multiplied by P. So let's see what we can do here. Now, with that scalar, right, remember one of our properties of matrix scalar multiplication is that I can multiply any of these things that I want by lambda, right? Not all of them, but just any one of them. So what I'm going to do is I'm going to say it's P inverse, and then I'm going to put lambda I there, and then P there. And then here's what we can do. We can now factor. So I can factor out the P inverse on the left and factor out the P on the right, so it looks like this. So this is the determinant of P inverse, and then let me do, let me do square brackets here. So then I'll have, so I'm going to take out the P inverse on the right, so that's going to leave A here, and then I'm also going to take out the P inverse on the left, and then P on the right. So it looks like this. Put my P there. And then use the same property of determinants that we used earlier, right? Because now this is a product. So this is the determinant of P inverse times the determinant of that thing in the middle, A minus lambda I, and then times the determinant of P. And what happens again is that the determinant of P inverse multiplied by the determinant of P is going to be 1. So we end up having this, which is the determinant of A minus lambda I, and that is the characteristic polynomial of A. So if, and this is what we've shown, that, right, if they have the same characteristic polynomial, then they have to have the same eigenvalues, right? So let me just write it like this. So if A is similar to B, we can say that the spectrum of A is the same as the spectrum of B, right? And there are other properties too that they share, right? Eigenvectors, however, is not one of them. So we can have similar matrices that don't have the same eigenvectors, but lots of the numerical properties and so forth. You know, so even something simple like if A and B are similar and one of them is invertible, then the other one has to be invertible, etc. All right, so lots of properties in common, but not everything in common. Okay, so let's now switch to that other word that was in our title, this idea of diagonalization. Pretty big word. I mean, imagine trying to fit that on a Scrabble board. But here's how we define what it means for a matrix to be diagonalizable, like it can be diagonalized, right? So a matrix A is, let's write this down, diagonalizable. Again, if and only if A is similar to a diagonal matrix. So if A is similar to a diagonal matrix. Interesting, right? So that's what it means. So then it's basically this. A would be similar to D, where D is diagonal. And then if we apply our definition of similar, right, then we would say that, so I'm going to write it like this, that A can be written as P inverse times D times P, where again, D is diagonal. Right, so D is diagonal. Right. Now, when you think about this, why is this important? Well, think back to a lot of the operations that we've done, going, starting with just, basic matrix operations up to things like eigenvalues and so forth, and, determinants and invertibility. For diagonal matrices, it's so easy to compute those things, right? Even something like finding a diagonal matrix raised to a certain power. All you end up doing is just raising the entries on the main diagonal to that power. You don't have to do the really complicated matrix multiplication. So if our matrix A, which is not diagonal, right, if it happens to be similar to something that's diagonal, then it's almost like A would inherit some of those algebraic properties, just like, if your you know, you're like, let's say you have a cousin and your cousin is like famous, right? You might become a celebrity, a somewhat of a celebrity, just by association with that famous cousin of yours. That's kind of what this is, right? So A is not necessarily a diagonal matrix, but it's close relatives, right, with the one that is diagonal, right? And then again, let me just give you one idea now of, and I'll just use one matrix calculation, which we know can be tedious, right? So you have to think like big matrix, maybe big power, but let's say, in fact, let me not use too big of a power. So let's say I wanted to do something like a squared, and a just happens to be diagonalizable, right? It's similar to a diagonal matrix. So I would have an equation like this, which means I could then do all of this. You may say, well, goodness gracious, that's pretty complicated. Well, not necessarily. Well, let's write out what it means to square something, right? So you'll have a quantity P inverse dP, and then you have times itself. So you'd have that. And then look at what happens if we like simplify the middle part here, right? What happens if we group the product in this way, the P times P inverse will always become the identity. So the identity is in the middle, and we treat that like, you know, the number 1. So what happens is you end up having P inverse, and then you'd have D times itself, and then P, which then reduces to P inverse D squared P, right? So what happens is, as far as the matrix multiplication that is concerned on this side, if you're squaring A, you end up squaring the diagonal matrix, which is a lot easier, right? So this is an easier power to do, right? And this one, not so easy, right? So it's not so easy. I can't even spell the word easy. It's not easy to spell easy. And but then in general, you can continue this process again using this idea of induction. And you could have something like a to the n would simply be P inverse times D to the n times P. So when you think of how tedious it would be to again, think about doing this stuff by hand. I'm not talking about using technology, right? Because underlying a lot of the technology that we kind of take for granted is properties like this, right? Properties like this that you can actually use to build more efficient ways to do things like, you know, invert a matrix, or in this case, raise a matrix to a certain power. But yeah, you can replace this more difficult matrix computation with this one, which is a lot easier, and then we can then do our basic P inverse times whatever this works out to be times P, right? So this is just one example of something rather basic, where if we have a matrix that can be diagonalized, in other words, we have a matrix A that is similar to a diagonal matrix, then it can make some of our matrix computations a lot easier, right? So kind of two little things that this video introduces: the idea of similar matrices, and then matrices that can be diagonalized. In the next video, we're going to look at, okay, how do we find the, you know, what are some of the conditions that guarantee that A can be diagonalized? And then if it can be diagonalized, how do we find the D? How do we find that special diagonal matrix? And more importantly, how do we find this P and its inverse, right? So that's what we're going to explore in the next video. I'm excited. Hope you're excited. Let's hop on over right now.